Okay, we're going to start. So as I said, I'll give your test back at the end of class, and then we'll talk a little bit about it, and maybe the next class talk a little bit about it again. For now, that's where we are. We're actually going to move on. Talk some more about derivatives. I wrote some examples on the board for you to actually use the limit definition, which again was in this quiz. We actually did an example with x squared, but now let's do some other examples. So we're still in 2.3/2.4. Examples. Use the limit definition to find the derivative. I believe x squared we already did, so this one's done. But let's actually do some more. Y equals c, where c is a constant. Let's do y equals x, y equals the square root of x. Let's do y equals 1 over x. Let's do y equals 2 minus x squared minus 1 over x, which is a little bit more complicated than what was on the quiz just now, but let's actually do that. Let's do those examples. So this kind of problem is something you'll be expected to do in this class, and on the next test there will definitely be a problem that will require for you to do this. So let's just actually crank out some examples really quick. In terms of the level of difficulty, it shouldn't be too difficult at this point to do this because it is using the difference quotient, which since day one we've been kind of crunching through those guys. They're just one extra step after the difference quotient, in which case we're taking a limit, and that's what yields the derivative. So recall that f is a function, f prime is one of the notations that gives us the derivative, and on the quiz you were asked to give me that definition. So what's that definition? F prime is? Limit as h approaches 0. F of x plus h minus f of x over h. So that was the answer to problem 1 in the quiz. You should have written down that limit. So it's a very important limit. The limit of the difference quotient as the denominator goes to 0. This actually gives you the derivative. So one thing you can remember that gives you is the slope of the function f. It's also the slope. It's equivalent to the slope of the tangent line. To f at the point x. It's also the rate of change of the function. So we already looked at slope as a measure of rate of change or speed or velocity. And so once we can find the slope of something, we can think of that as a rate of change of the thing. Okay, cool. So with this interpretation in mind, here we don't have to interpret anything. We just actually want to compute the functions from this formula for these guys. So let's actually move on to B. Y equals c. So that's our f of x here. So this means that your f prime of x is equal to limit as h approaches 0 of f of x plus h minus f of x over h. Now, especially if you don't have this formula memorized by now, I would suggest that every time you're using it, write down the general formulas, because you will eventually need to memorize it. I'm going to ask you the definition again on future tests and quizzes. So in this case, let's actually plug these guys in. So if your f of x is a constant, what is f of x plus h? Yeah?
It will be 0.
No. If f of x is c, what is f of x plus h?
C plus A.
It's c, right? So constant itself is going to be the same thing, right? There are no x's to plug in, so it doesn't change. Similarly, f of x is c. So this just gives you the limit as h approaches 0 of 0 over h. Well, that's just 0. In other words, this we can actually take as a general rule. That I'm using Leibniz notation here to write it down because it's more concise that way. The derivative of a constant is 0. This you can now take as a general rule. It's something that you can apply without justifying it. Okay, so from now on we can actually do that. And so when you see something, let me just remind you of this notation here. When you see dy dx, or that's the same as d dx of a function y, it just means the derivative of y with respect to x. So this means that when you see d dx of c, that just means the derivative of c with respect to x. Okay? So this is how I can state the rule. The derivative of a constant is 0. Another way you can interpret that, based on our interpretation, is if you have a constant function, what does its graph look like? Well, it's going to be a horizontal line that passes through that number, right? And what's the slope of a horizontal line? Well, it's 0, right? So the derivative is supposed to give us the slope. It makes sense that the slope of every horizontal line is going to be 0. Therefore, it makes sense that the derivative of any constant should be 0. And now this is something that we can just take as fact. In fact, it is something that I highly recommend that you memorize. It's just a fact that we know now. Okay? And it's not that hard to prove. Just plug into the limit definition and 0 pops out because there's literally nothing to do. Not too much to do here either, but let's just run through that just so we can have another rule under our belts. So here's our y is equal to x. So right now what I want to do is find f prime. So again, that's just the limit as h approaches 0 of f of x plus h minus f of x all over h. In this case, if my y is x, which I'm thinking of as f of x, what is my f of x plus h? So just x plus h. Replace all x's with x plus h. Minus my f of x is the original function. I'll put it there. All over h. So here, this is easy to simplify. The x's just kill each other. And so I have the limit as h approaches 0 of h over h. So that's just the limit as h approaches 0 of 1. That's just 1. So it turns out the derivative of x is actually 1. Now that's something that's nice to know. I will be giving you a more general rule regarding things like this called the power rule, which you can apply here. But it's nice to know that the derivative of x is 1. It shows up often enough for you to actually just know that and memorize that as a rule. And again, that makes sense. If you're looking at y equals x, then the coefficient is 1. The slope of the function y equals x is 1. Let's get to something that's a little bit more complicated. Let's actually figure out what the derivative of something like radical x is. Here's my y equals radical x. I want to know what is y prime. It's just the limit as h approaches 0. F of x plus h minus f of x over h. This was just the limit as h equals 0 as h approaches 0. So if my y is radical x, what is f of x plus h?
X plus H.
Radical of x plus h, all under the radical, minus my f of x, radical x, over h. How do we simplify something? Yeah?
Multiplied by the conjugate.
Multiply the conjugate over itself. That's our standard rule for simplifying a sum where there's a radical in one of the parts at least. So I multiply by the conjugate, which is just I change the middle sign over itself. So the top, when I multiply this out, it looks like the difference of squares. This is a minus b times a plus b, so that just becomes a squared minus b squared, and that gets rid of the radicals. Over, now in my denominator, I just have that. The top, my x's kill each other. So I have the limit as h approaches 0 of h over h times this guy. Now my h's cancel. So I have the limit as h approaches 0 of this guy. And at this point I can plug in h equals 0, my denominator won't be 0. So what would I get here? Plug in 0, that just gives me radical x. So this is just 1 over radical x plus radical x. Or in other words, 1 over 2 square root of x. So now that can be a rule that we know. The derivative of the square root of x is 1 over 2 times the square root of x. But again, I'll give you another general rule that will cover that as well. But that won't be in this class. So if your function is radical x, then the function that tells you its slope at any point will be this function, 1 over 2 radical x. Yes?
Shouldn't it be negative 1 over 2 radical x?
Where did the negative sign come from? Nope, it's 1 over 2 radical x. We didn't do anything weird with the signs here. That was a plus h, which gives us a plus h, and that cancels. So that's it, 1 over 2 radical x. Like, is this okay for everyone? We're okay, right? Because we've been doing this a lot. So literally everything except the limit part we've been doing. Before though, we would have stopped at this point, and that was it's fully simplified. But now we go one extra step by plugging in that h equals 0, and that gives us something called a derivative. Let's do e. F is going to illustrate a nice property that we'll use later, so I'm going to do that as well. What if my function is 1 over x? What do I expect the derivative to be? It's the limit as h approaches 0 of f of x plus h minus f of x h. Limit as h approaches 0 of, if I find f of x plus h here, let's just replace each x with x plus h, so that's just 1 over x plus h minus the original function, which is 1 over x all over h. How do we simplify something like this complex fraction? How do you simplify a complex fraction? What?
The common denominator.
The common denominator, the LCD,
yeah.
And you multiply top and bottom by it. By the way, in the test, and I'll talk about this a bit later, I don't know if I'll discuss it at length today, but there was a lot of students had trouble with problem 1, which was just me asking you to simplify things. And in particular, the fraction part, where I asked you to simplify a fraction, a lot of people were making mistakes with that. And one of the reasons is they didn't really know what they were doing. They kind of, well, there were a couple last students, not a lot, but there were students who did things that they weren't supposed to do, like they'd expand parentheses too early, or they decide to expand the denominator, or they decide to do these things where technically from a mathematical standpoint they didn't do anything wrong, but it just made everything less efficient. It made their lives harder than it had to be, and so they ended up making a mistake down the road because they ended up with this huge complicated mess that they didn't know how to deal with. So one of the reasons, this is why I sometimes asking you, how do we simplify this? What is the strategy? How do we simplify this? What is the strategy? You should have these strategies in your head for how to simplify common things. No, if it's a complex fraction, multiply and divide by the LCD. That is the most straightforward way to do it. Do not do anything else, right? If you have a sum and one of the things have a radical in it, multiply and divide by the conjugate. Do not do anything else. If you have a fraction and you want to simplify it, what do? Factor the top and bottom and then cancel the common terms, right? So if you knew that, then expanding the parentheses as the first step would never be something you try. It wouldn't be something you would try. But I saw a lot of students who actually did that and made their lives harder, and some of them even did it incorrect, right? So it's very important that these are things that will show up all the time. You need to have like a clear strategy in your head for how to approach them. Something you can say in a very short sentence. If I see this, I do that, right? And that would have saved you guys a lot of trouble. But yeah, so you see a complex fraction, which is fractions inside of fractions. The quickest way to deal with that is to multiply and divide by the LCD. If you're doing something else, you're being less efficient and you're opening yourself up to mistakes. Okay, so we'll take this guy, and obviously we have to distribute here. Now in the first case, the x plus h's would cancel, and I'd be left with an x minus. In the second case, the x's would cancel, and I'd be left with an x plus h. Parentheses cause a lot of people trouble in the test as well. And when I give back the test, you'll see that. So if I ever write down parentheses and put an exclamation point, you will know that you'll know exactly what you did wrong. So a lot of people are on the right track, but then they didn't put in parentheses when they should have, and that kind of messed them up. So now here we have x minus x, and then we have a negative h. I saw a few people make mistakes like that as well. They forgot that they had to distribute a sign. So now what happens is the h's will cancel. And we have minus 1 divided by x times x plus h. You'll notice that now we can plug in h equals 0 without making the denominator identically 0. So this gives us minus 1 over x times x, or minus 1 over x squared. In other words, what we're saying is the derivative of something like 1 over x is minus 1 over x squared. So if this is your function, that is the function that will give you its slope at any point. So go with something like this. So here, this example is the first example that has several terms that we want to differentiate. All the time I was asking you to differentiate one function. Here we're differentiating a bunch of functions being added together. So let's actually look at something like that case. And this is kind of going to illustrate a rule that I'm going to tell you about in next class, called the sum rule for derivatives. So we know that to find the derivative, this is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. So we're going to just replace all x's with x plus h here. That's 2 minus x plus h squared minus 1 over x plus h minus parentheses. Put our original function back. All over h. Let's simplify a little bit here. So we can take 2, this will be minus x squared minus 2xh minus h squared by me doing FOIL on those parentheses here and distributing the negative sign. This will be minus 1 over x plus h. This will be minus 2 plus x squared plus 1 over x all over h. Now let's see what we can simplify here. The 2's would kill each other, the x squares would kill each other. Nothing else kills anything else. So we have the limit of minus 2xh minus h squared. This is also something that I recommend you do. Just strike things out once you're recopying them. I saw several people made that mistake of they wrote something down here, but when they moved to the next line, they forgot to copy that guy down. So kind of keep track of what you're moving down by actually striking it out once you've moved it down. We have the minus 1 over x plus h. So I'll strike that out. And I have that plus 1 over x. Strike that out. So now I know that I've taken care of everyone in the numerator, and so that's what I have. Now there's a couple ways you can approach this here. You can realize that you have a complex fraction, and so you can kind of multiply and divide by the LCD. But in this case, while that is pretty straightforward, it is somewhat of an overkill here, because notice that this part here, we don't really need that technique. So one way to kind of simplify the algebra for you, so you have to multiply out less, is we can actually split the fraction up. So I would kind of separate this part, which looks easier to deal with to me, and then split up the part where I use the complex fractions approach. So what I could do is this guy plus this guy. And this can work because of how fractions work. I can split a fraction across a numerator. We spoke about that in the first or second lecture. And then I can deal with each of these separately. So this is kind of illustrating a rule that I will tell you guys about next time, that if you're taking the derivative of a sum of functions, you can actually take the derivative of each function individually, and it gives you the same answer. And the reason is because we can split fractions. Right, so we just want the limit of this one. So in the first situation, we know how to deal with that. I just factor up that h. And that's going to cancel. In the second situation, this is a complex fraction, so I'll do that rule here. Multiply by x times x plus h. So now this becomes minus x minus h, plus this guy would be minus x plus x plus h over h times x plus h. The minus x will kill that guy. And then what I would have is I would have an h left on top and that will cancel that out. And so now, basically, I have the limit as h approaches 0, minus 2x minus h plus 1 over x times x plus h. And at this point, I can plug in h equals 0 without any division by 0 happening anywhere. And so that would be minus 2x, h is 0. Here I plug in h equals 0, plus 1 over x. Now this particular kind of example is a kind of example that if I ask you about using the limit definition to find a derivative, more than likely it will be some function like this. It will be a sum of functions where you really have to know your algebra to navigate. It's an important thing to know how to do it. So again, this is another illustration of, this is the calculus. This is where the definition of the derivative comes in, which is all the calculus. Literally everything else was a bunch of algebra, right, to get to that answer, right? And once you get to this answer, then calculus takes over again, and you can put an interpretation on it. You can talk about, oh, it means the slope, or it's talking about how fast this function is moving. And you can do a lot of things with this function itself. But most of the in-between was algebra. Going to be quite typical. We'll stop there. We're still not done with this section. Next time we'll do a couple more examples and talk about some more important concepts. Then I'll give you some rules. So right now I'll return your test.
Thank you very much.
You're welcome.